Okay, this is Chapter 14, Acids and Bases, Lesson 3. Today we're going to discuss polyprotic acids, acid-base properties of salts, and calculations with salts. So let's get started. Calculating Ka from percent dissociation. Lactic acid, which is that product that builds up in your muscles when you exercise, leads to pain and a feeling of fatigue. If I have a 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. So from that information, you need to calculate the Ka for that reaction. The first thing we want to do is write our percent dissociation equation. So it's percent dissociation equals part over whole times 100. You know what your percent dissociation is. It's 3.7. You don't know what your part is, but you definitely are given your initial concentration, which is your whole, which is 0.1 molar times 100. In solving for x, we get x equal to 0.0037 molar. Now to figure our Ka, we need to set up an ice table. So lactic acid, which is HC3H5O3, is a weak acid. And how do I know it's weak? Because it's not one of the 6 strong that you had to memorize. Is going to dissociate into H plus and C3H5O3 minus. We know that our initial concentration is 0.1, and we know that we have no hydrogen ion concentration or C3H5O3 minus concentration. What we do know, however, is that at equilibrium we have present in solution 0.0037 molar of our 2 ions. What this allows us to do then is, now that we know what X is, we can figure in the rest of our table. So we know that the ions were plus X, so these are 0.0037. And we know that as lactic acid dissociated, this side is going to be minus 0.0037. So 0.1 minus 0.0037 gives us 0.0963. In setting up our Ka expression, we know that Ka is equal to the concentration of H plus times the concentration of C3H5O3 minus over the concentration of lactic acid. So solving for our Ka, we can substitute in our equilibrium expressions. So technically we're going to have 0.0037 squared over 0.0963, which leads us to a Ka of 1.42 times 10 to the negative 4. That should make sense because lactic acid is a weak acid, so its Ka should be small. Let's take a look at polyprotic acids. First of all, poly means many. Protic refers to protons, so it refers to many protons. What we're talking about here is an acid that is either monoprotic, diprotic, or triprotic. For a monoprotic acid, we have 1 proton, and if we were to write a dissociation reaction, it would simply be HA dissociates into HA plus and A minus. A diprotic acid has 2 protons. So what we're talking about, if you think about something that's got 2 protons, it's going to have the form H2A. So your anion had to have a negative 2 charge, your proton had a positive 1 charge. When you dropped and crossed, you got H2A. Now when this dissociates, you can only remove 1 H at a time. So your first step, if this is my first step, is going to just remove 1 H. So I'm going to have H plus and HA minus. In my second step, I'm going to start with the product of HA minus, and I have H plus A2 minus. I bet you can guess what a triprotic acid is. 3 protons, and the removal of those 3 protons has to happen in 3 steps. Our general formula for our acid would be H3A, PO4 minus, PO4 3 minus, and when you drop and cross, you'd have H3PO4. So in our first step, we're going to remove the first proton, so you'd have H plus and H2A minus. In our second step, you'd start with your product, H2A minus, yields H plus HA minus. And in our third step, you would remove the last proton, so HA minus, this should be 2 minus, sorry, and this would be A3 minus as you remove each proton. So what is the relationship between the value of Ka1 versus Ka2 versus Ka3? Well, Ka1 is going to be much, much greater than Ka2, which is going to be slightly greater than Ka3. So there's a large disparity between Ka1 and Ka2, and a very small amount between Ka2 and Ka3. So what this means is that really, when you have a polyprotic acid and it dissociates, that you're really removing most of the hydrogen that's going to make a difference in a reaction with the first Ka value. So to see exactly how this works, we are going to calculate the pH and concentration of all species in a 3 molar solution of phosphoric acid, H3PO4. You would never be asked to do this on an AP exam, but you need to see how, in a stepwise fashion, the different Ka values affect the pH. So in our first step, as I said, we're starting with H3PO4, and in this first step we're only going to remove the first hydrogen. So we have H plus and H2PO4 minus. And in setting up our ice table, we know that our initial concentration is 3 molar. We have 0 of these. These are going to be minus X plus X plus X. 3 minus X, X, X. Our Ka1 from the chart is equal to 7.5 times 10 to the minus 3, and that's equal to the concentration of H plus times the concentration of H2PO4 minus over the concentration of H3PO4. So what that gives us is 7.5 times 10 to the minus 3 equals x squared over 3 minus x. So you're going to put that in your solver, and when you solve for x, you're going to get 0.146 molar, which is the concentration of H plus and subsequently the concentration of H2PO4 minus. So we can say that this is approximately 0.15 molar. Okay, going to step 2 now, we're going to start with our product, which was H2PO4 minus, and we are going to remove a hydrogen, and we're going to be left with HPO4 2 minus. In setting up our ice table, we have to include what we learned in step 1 in our ice table. So our initial concentration of H2PO4 is 0.15 as determined by the last reaction. We also have 0.15 molar of H plus in solution already from the first step, and we don't have any concentration as of yet of the HPO4 2 minus. So as the reaction proceeds, minus X plus X plus X. So this is going to be 0.15 minus X, 0.15 plus X, and X. Our Ka2 is equal to 6.8 times 10 to the negative 8, which is equal to the concentration of H plus times the concentration of HPO4 2 minus over the concentration of H2PO4 minus. Substituting in, I have 6.8 times 10 to the negative 8 is equal to 0.15 plus x times x over 0.15 minus x. Putting this into our solver, we get x equal to 0.15. X is equal to 6.2 times 10 to the negative 8 molar, and that's equal to our HPO4 2 minus. Now, at this point, you can see the H concentration, as you recall, is going to be, the H concentration is going to be equal to 0.15 plus X. Now, I think you can make the intuitive leap here that given that X is 6.2 times 10 to the negative 8th, that's an extremely small value and will really not affect the 0.15 molar to begin with. So essentially, my H plus concentration stays at 0.15 molar. Going into step 3, which is the removal of the last hydrogen, I have HPO4 2 minus, which dissociates into H plus, and PO4 3 minus. Let's look at my ice table. So my initial concentration of HPO4 2 minus is coming from my last calculation, which is going to be 6.2 times 10 to the negative 8th. We have, as we said, 0.15 molar in solution, as it was unaffected by the last dissociation. We have no PO4 3 minus as of yet. So this is minus x plus x plus x. 6.2 times 10 to the negative 8th minus x, 0.15 plus x, and x. In my Ka3 is equal to 4.8 times 10 to the negative 13th, extremely small, and that's going to be equal to the H plus concentration times the PO4 3 minus concentration over the HPO4 2 minus concentration. So my Ka3 equals 4.8 times 10 to the negative 13th equal to 0.15 plus x times x over 6.2 times 10 to the negative 8th minus x. Putting all of that into my solver, I get an x equal to 1.98 times 10 to the negative 19th molar, which is equal to my PO4 3 minus concentration. And we know that my H concentration is still approximately 0.15, because this number is even smaller. This x value, 0.15 plus 1.98 times 10 to the negative 19th, is going to have no bearing on the molarity, and therefore is 0.15. Now, they want the pH, so we're going to take the pH is equal to the negative log of the H concentration, which in this case is the negative log of 0.15, and that's going to equal 0.82. So there's my pH. They also want all species in concentration. So we have to go back. We know that our H plus is 0.15 molar, even though it's really 0.15 molar plus 1.98 times 10 to the negative 19th plus 6.2 times 10 to the negative 8th. It's really not going to change. My PO4 3 minus we just calculated as 1.98 times 10 to the negative 19th molar, and my HPO4 2 minus is equal to 6.2 times 10 to the negative 8th molar, and my H2PO4 minus is equal to, as we calculated in step 1, 0.15 molar, and my H3PO4 is equal to 3 minus X, which is going to be equal to 2.85 molar. So those are all the concentrations. Next, we're moving on to acid-base properties of salts. You talked a little bit about this in the first homework set. Salts that produce basic solutions. Examples: salts of weak acids. So recall that salts are ionic compounds comprised of a metal and a nonmetal. So if we were to take acetic acid, and you know that this is a weak acid, if we were to remove the H plus and add a metal cation, of a strong base, then we would get something like this. We would get NaC2H3O2. If we were then to drop this in water, okay, so if I put this in water, what's going to happen is it's going to separate into its respective ions. So in water, I wind up having Na plus, and I wind up having C2H3O2 minus. Now the sodium has no bearing here, okay, but my C2H3O2 minus ion in the presence of water, and I'm going to rate this as HOH for a reason, is going to form acetic acid again and OH minus. So this is my acid, and this is its conjugate base. So acid conjugate base. And then I have my OH minus in solution, which means that this is going to be a basic solution. So what happened is, in order to form a basic solution, a salt that produces a basic solution, you're going to need a weak acid anion with a strong base cation. And remember that HA is always the generic form of our acid, and its partner is going to be A minus, which is base. And these always appear, okay, on opposite sides of the reaction. And then we can use Ka times Kb equals Kw to figure out any other things that we need to before we proceed. So conversely, when we talk about salts that produce acid solutions, we're going to talk about mixing a weak base cation and a strong acid anion. For example, NH3 is a base. Its conjugate acid would be NH4 plus. Therefore, if I had NH4Cl, this would be a salt that produced an acidic solution. The NH4 comes from the weak base, the Cl comes from the strong acid HCl. So if these were to dissociate and be placed in water, I would get NH4 plus and Cl minus. I'm not interested in the Cl minus, I'm interested in the NH4 plus, and I'm going to mix that with water, and I'm going to get H3O, which is acidic hydronium, and NH3. So this is an acidic solution. Okay, let's do some calculations with salts. So in this problem it says, what is the pH of a 0.14 molar solution of sodium acetate? Well, first of all, when we write sodium acetate, NaC2H3O2, we have to realize what we have here. We have a weak acid with a strong base cation, which means that it's going to be basic. In solution is the acetate ion C2H3O2 minus plus HOH is going to yield HC2H3O2 plus OH minus. So if we were to create an ice table for this situation, we would be starting with 0.14 molar. We're not worried about water because it's pure. This is going to be 0, 0, minus x plus x plus x. So 0.14 minus x, x, x. So we're dealing with a basic solution here. So we have to remember that we're no longer dealing with Ka but with Kb. The Kb is equal to 5.56 times 10 to the negative 10. You get that from your Kb table. And that's going to be equal to the concentration of HC2H3O2 times the concentration of OH minus over the concentration of the acetate ion. 0.56 times 10 to the negative 10 equals x squared over 0.140 minus x. When I put that in my solver, I get x is equal to 8.8 times 10 to the minus 6. This is equal to the OH minus concentration. It's also equal to the HC2H3O2 concentration. So now that I have the OH minus concentration, I cannot calculate the pH, but I can certainly calculate the POH, which is equal to the negative log of the OH minus concentration. So POH is going to be equal to the negative log of 8.8 times 10 to the minus 6. So I'm going to get a POH equal to 5.06. That means that my pH after subtracting from 14 is going to be 8.94. So we've found our pH. Please remember that in order, if you don't have the Kb, so this is a side note, if you don't have the Kb, you know that the Kw is equal to the Ka times the Kb. The Kw of water is 1 times 10 to the negative 14th. You certainly know the Ka of acetic acid, which is 1.8 times 10 to the negative 5th, times the Kb. So therefore, you can solve for the Kb if you're not able to look it up and get 5.56 times 10 to the negative 10. This again refers to the partner concept of acid-base conjugate pairs. Okay, another problem. I'm going to change this problem actually. We're going to change it to, this isn't actually just not a good choice. We're going to get rid of the dimethylamine and we're going to change it to C2H5 2NH3Cl. Okay? So, a couple of things. Don't let the size of the molecule scare you. This is just like looking at NH4Cl, where this is the base part and this came from the acid. So this whole thing basically came from the base and the Cl came from the acid. We are starting with C2H5 2NH3. We got rid of the Cl because we don't care about the Cl in solution, and we are adding H2O to that, and we're going to form H3O, and we're going to form C2H5 2NH2. And you might say, well, how is it NH2? The NH3 donated an H to the H2O and became NH3 base, and this is my conjugate acid. So looking at our ice table, we're starting with 0.14. We're not worried about this. This is 0, this is 0, minus x plus x plus x, 0.14 minus x, x, x. So we have to figure out what our So what we have to realize here is that we had initially a weak base with the anion of a strong acid. So this is going to be a slightly acidic solution, which we know it is as of the formation of H3O. We also know that Kb equals Ka times Kb. So 1 times 10 to the negative 14th. We don't know our Ka. The Kb of the dimethylamine, if we look that up in the chart, is going to be 1.3 times 10 to the negative 3. In solving for Ka, we get a Ka equal to 7.69 times 10 to the minus 12. Just looking at this Ka tells us this is an extremely, extremely weak acid. So our Ka equals the concentration of our H3O plus times the concentration of our C2H5 2NH3 over the concentration of our dimethylamine. So Ka equals 7.69 times 10 to the minus 12, which is equal to x squared over 0.14 minus x. When we put that in our solver and we solve, we're going to get x equal to 1.04 times 10 to the minus 6 molar, which is the concentration of our H3O plus. From that, we can take the negative log and get a pH equal to 5.98. Okay, so now we're going to predict whether an aqueous solution of each of the following salts will be basic, acidic, and neutral, and using the information that we just learned. So looking at the first one, we're looking at ammonium acetate, and let's see what we can discern from looking at this. First of all, you have the NH4 plus ion, which is a weak conjugate acid, and it comes from a base, NH3, which is a weak base. Now, what do we know about this weak base? Well, we know that it has a Kb equal to approximately 1.8 times 10 to the negative 5. And what that means is that since the pH scale is 14, we can see, if we just get rid of the numbers and we just look at the exponents, 10 to the minus 5, then our weak conjugate acid had to have a Ka ending in 10 to the minus 9. Because 10 to the minus 9 and 10 to the minus 5 gives us 10 to the minus 14. So that's looking at the first part of it. In the second part of it, we have the acetate ion C2H3O2 minus, which is a weak conjugate base from the weak acid HC2H3O2. If we look at the Ka of acetic acid, it's also 1.8 times 10 to the minus 5. So again, our Kb here would be 10 to the minus 9. So essentially what we are looking at is this side. So we've got a Ka of 10 to the minus 9. We've got a Kb of 10 to the minus 9. So solution A is neutral. Now, the other thing that you can see here, another way that would lead you to believe that it's neutral, is that acetate ion comes from acetic acid, which is a weak acid. The ammonium ion comes from a weak base, which is ammonia. So you have weak and weak, which is going to be neutral. Let's look at B down here. We're looking at NH4Cn. And what do we know? Again, we've got NH4 plus, which is going to be my weak conjugate acid of a weak base, NH3. Those are partners. And we just said that the Kb here was going to be 10 to the minus 5, which meant that the Ka is 10 to the minus 9. And I just got that information from the problem that we did in A. Now let's look at Cn. The Cn minus ion is a weak conjugate base of a weak acid, HCN. So this is a weak acid. And we can find the Ka of this weak acid. We can look this up, and we know it's 6.2 times 10 to the minus 10. And we're just interested in the exponent, so that means that the Kb here is going to be 10 to the minus 4. So when comparing the Kb and the Ka, 10 to the minus 9 to 10 to the minus 4, we can see that the Kb is greater than the Ka, so therefore this solution would be basic and would have a pH greater than 7. So B is basic. I'm going to change aluminum sulfate because I want to be able to show you one of each. I'm going to change this to NH4F in choice C. So in choice C, we have NH4F. I'm not going to reinvent the wheel. This is going to be NH4 plus, and that's the weak conjugate acid. NH3 is the weak base. We've already ascertained several times that this is 10 to the minus 5. This is the Kb, and the Ka here is 10 to the minus 9. So now we're looking at F minus. F minus is a weak conjugate base, which comes from HF, which is a weak acid. How do I know it's a weak acid? Because it's not one of the 6 strong that I told you you have to memorize. So when I look up the Ka of hydrofluoric acid, it's 7.2 times 10 to the minus 4. Again, I'm only interested in the exponent, which means that the Kb of F minus is going to be approximately 10 to the minus 10. So now when I compare my Ka and my Kb here, I have 10 to the minus 9 versus 10 to the minus 10. So therefore my Ka is greater than my Kb, and this would be an acidic solution with a pH less than 7. So this was acidic. And that basically, this little table here sums that up. When the Ka is greater than Kb, the pH is less than 7, it's acidic. When the Kb is greater than the Ka, the pH is greater than 7, it's basic. And when the Ka equals the Kb, it's going to be neutral. Let's talk about the effect of structure on acid-base properties. This comes up once in a while. You might see one multiple choice question on the AP exam about this. So when we talk about polarity, we're talking about a positive, negative end on a molecule. So more polar equals stronger bonds. So what you can see in this first chart here is that HF has a very huge bond strength, so it's got strong bonds, yet it's weak in acid. So this would be more polar at the top, going toward less polar. And what we know is that this should make sense to you because strong acids have weak bond strength. Why? Because strong acids have weak bond strength because strong acids dissociate or ionize in water, and therefore they have weak bonds. I want to talk about oxyacids. Acids that contain oxygen in their anion. So you can see in the chart here that the more oxygens you have, the larger the Ka. So more oxygen equals a stronger acid. Now I want to use an example to explain this. If we look at HClO4, it looks like this. You have all these O's on one side that's going to make this very negative and very polar, which means that this bond right here between this H and O is going to be a very weak bond. So you can see that the more oxygens you have, the more polar something is, the stronger it is. This was HClO4. Let's compare that to HOCl, in which here, this is a very strong bond, but it is a very weak acid because it does not dissociate in water. Where here, this was a very strong acid, so it will dissociate in water and therefore weak bonds. So we have some acid-base properties. So this is acid-base properties of oxides. And we actually learned these in another unit. We already talked about this when we did reaction chemistry. So metal oxides plus water are going to yield a base. An example of this would be K2O solid plus water is going to yield 2KOH aqueous. Or we can do it like this, K2O solid plus H2O liquid is going to yield 2K plus aqueous plus 2OH minus aqueous. Another example might be Fe2O3, so iron 3 oxide and water is going to yield FeOH3 3. And I believe this is actually, I believe iron 3 hydroxide might be a solid. Well, it's only slightly soluble, okay, but it proves the point of metal oxides and waters forming bases. And then non-metal oxides, we also discussed this. Non-metal oxides and water produce acids. And a couple of examples of that would be P2O5 plus 3H2O yields 2H3PO4. Another would be SO3 plus H2O yields H2SO4. However, in this one, there's a subsequent reaction going on, okay? Actually, even in the H3PO4, where the SO4 is going to dissociate. So this is going to H2SO4 is going to dissociate and react with the water and break down into H plus HSO4 minus. This is in an aqueous solution, so it automatically reacts with the water, so this subsequent reaction takes place. And I just want to point out that SO3 gas is not the same as the SO3 2- ion. Some students interchange them. Okay, so that finishes our acid unit.